Every software manager faces the exact same problem on day one. You have a rough estimate of the software's size, but your stakeholders want to know the budget, the timeline, and the exact number of developers required. Basic COCOMO solves this using only one mathematical input, kilo lines of code, or KLOC. From that single number, the model calculates the rest of your project parameters. The most crucial parameter it calculates is effort. Effort is the total volume of work required, measured in person-months. This diagram shows exactly how that works. One developer working for 6 months generates 6 person-months of effort. If you assign 3 developers to the same task, they can finish it in 2 months, but the total work remains exactly 6 person-months. Effort measures the absolute volume of labor your project requires to exist. It is completely independent of how you arrange that labor on a calendar. To turn your KLOC estimate into a working schedule, Basic COCOMO uses a specific mathematical pipeline. We move from KLOC to effort to time, and finally divide effort by time to get our people, or team size. First, effort equals constant A times KLOC to the power of B. Next, development time equals constant C times effort to the power of D. Finally, team size is just effort divided by time. You'll notice variables A, B, C, and D in those equations. These are constants, and their exact numbers depend entirely on which category your software project falls into. This table shows the specific values Barry Boehm derived from studying real-world projects. Look closely at the A and B columns. As we move down the rows from standard organic projects to semi-detached, and finally to highly constrained embedded projects, the numbers get larger. The increasing values act as an objective mathematical penalty. Because a real-time embedded system is far more difficult to build than an organic accounting software, these larger constants automatically scale up the required labor in the final equation. Let's plug real numbers into the organic baseline. For a 32 KLOC organic project, we set up the effort formula using our table constants. That gives us 2.4 times 32 to the power of 1.05. We solve the exponent first, getting 38.1. Multiply that by 2.4, and we have a total effort of 91.4 person-months. With effort established, we calculate development time. Using our C and D constants for organic projects, we multiply 2.5 by 91.4 to the power of 0.38. That results in roughly 13.9 months on the calendar. To find our team size, we divide our 91.4 person-months of effort by our 13.9 months of time. The math gives us 6.6, meaning we need a team of exactly 7 developers. Let's test this out. Try calculating the effort for a semi-detached project with a size of 50 KLOC. Use the table constants in your head. Setting up the formula with semi-detached constants, you multiply 3.0 by 50 to the power of 1.12. Resolving the math gives you a final requirement of 239.4 person-months. By using these formulas, you replace subjective guesswork with a concrete mathematical model. When a stakeholder asks why a project requires 239 person-months of labor, you have the exact calculation to back up your schedule. Let's look at a side-by-side comparison. On the left is our 50 KLOC semi-detached project, requiring 239 person-months. On the right, we calculate a smaller embedded project of only 40 KLOC. Using the embedded constants, 3.6 times 40 to the power of 1.20 evaluates to a staggering 301.7 person-months. Notice the discrepancy. The embedded project contains 10,000 fewer lines of code, yet it requires over 60 additional person-months to complete. The strict reliability and hardware constraints of embedded systems drive up the labor dramatically. This brings up a common interview question. If more lines of code require more work, why does COCOMO use an exponential formula instead of a simple linear multiplier? Here's a diagram showing communication paths in a team. With 2 developers, there is 1 line of communication. Grow the team to 4, and you have 6 paths to manage. Expand to 8 developers, and you now have 28 distinct integration points. The complexity does not scale linearly. COCOMO's exponential constants mathematically model this exact dynamic. They account for the compounding friction of testing, integration, and management overhead that naturally occurs in large technical groups. With effort calculated, multiply your 100-person months by an average 80,000 rupee salary to get an 8 million rupee labor cost. To find the true total, you must add hardware, software licenses, and testing tools. Basic COCOMO is highly effective for preliminary planning because it is easy to apply. However, it relies entirely on your KLOC estimate. It assumes every developer has the same experience level, and it completely ignores modern development tools and hardware constraints. While basic COCOMO gives you a mathematically sound starting point, its blindness to environmental factors limits its precision. To get accurate estimates for complex modern projects, we need to adjust our math for the reality of the workplace. That requires stepping up to intermediate COCOMO.